We're now on to the final bit of chapter 4. So chapter 4 has been all about moments, and we are now on to this last bit, which is to do with tilting. And it says, when a rigid body is on the point of tilting about a pivot, the reaction at any other support is 0. And so what that really means is, if I've got, imagine here's my beam, and I've got some supports like here and here. Now, normally, what we're used to is we have a reaction force from both those supports, and we also have the weight of the beam coming downwards. But if I apply a force to this end of the beam, what we can expect will happen is the beam will at some point start to tilt. And at the moment that it starts to tilt, this reaction force here, if it's tilting about that pivot, then the reaction force here will go to 0. And I want to demonstrate this using my ruler. So if you just have a look at what I've got here. So here's my beam going across, and these are my two supports that are on the beam there. And what we're saying is, if I apply a force to this end here, you can imagine what's going to happen. As I push down on this end, the beam will start to tilt, and it's tilting about this support here. That's where the rotation is occurring. So as I push down, the beam is starting to lift off the support there. So any reaction force from that support will be going to 0. So on the very point of tilting, as it's just about to leave that support, the reaction force is equal to 0. The same sort of idea can be looked at if we've got a beam which is suspended. So here's my beam, and it's being held up by these two wires, we'll call them, and it's the tension in those wires that is holding the beam up. Now, you can imagine if I'm going to push down on this end here, if I apply this force, the beam will start to tilt. And it's tilting about that point. That's where the rotation is happening, about here. Now, as it starts to rotate, we can see that this wire, as such, starts going loose, it's going slack. And so the tension in that wire goes to 0. So at the very point of tilting, the tension there is going to 0. Same sort of idea as the reaction force on the beam with the supports. So let's solve some tilting problems. So we're going to do example 11, which is about a uniform beam AB. So uniform AB, it's got mass 45 kilograms, 16 meters long, and it rests on these supports C and D, where this length is 5 meters, this length is 2 meters. And a child stands on the beam at A. So we're going to have a child standing over here, and it's causing the beam to start tilting, and it's tilting about this point. So we know that the reaction force at D is going to go to 0. So let's draw ourselves a better diagram. So here's my beam. I've got the support at C and the support at D. This is end B, this is end A. And if we're thinking about the forces, well, we've got the weight of the beam. It's uniform, so that 45 will act in the very middle of my beam, 45G. We've also got the mass of the child. So the child stood on end A. So their weight is coming downwards at end A. And I'm going to call their mass M. That's what we're trying to find out. And then we've also got the reaction force at C. So reaction at C. And remember, because we're on the point of tilting, there's no reaction force at D. That reaction force has gone to 0. Let's just put some measurements on here so we know that that distance there is 5 meters. Also, the distance from C to the center of the beam, well, the whole beam is 16 meters long, so that must be 3 meters to get to the middle. And now what we can do is we can take moments about C. So I'm going to take moments about this point here, and I chose that point because then I don't even have to work out the reaction force at C. That's not going to be included in this moment calculation. So taking moments about C, I know that the moments going clockwise will equal to the moments anti-clockwise. So going clockwise, what have we got? We've got this 45G and it's at a distance of 3 meters. So the moment clockwise, 45G multiplied by 3. And that's equal to the anti-clockwise moment, which is this force mg and multiplied by the distance 5 meters. So nice and easy then. I just have to rearrange this to find out what m is, so we can cancel the g's straight away. So we're going to get that m is equal to 45 times 3 and divided by 5. So that will be m is equal to 27 kilograms. So I've calculated that the mass of the child is 27 kilograms. And so what we did there, the main new thing that we've just learned is that we were told the beam is on the point of tilting and it's tilting about the point C, which means that reaction force here will go to 0 as the beam is about to lift off in its tilt. Okay, the next example is what I just mentioned in terms of the tension forces. So we're talking about a rod that is suspended this time using some wires. So we've got a non-uniform rod, a length of 10 meters, a weight of 40 newtons, suspended from a pair of light cables attached to C and D. They've given us some distances, and then a weight of 25 newtons is hung from one end and the rod is on the point of rotating. Right, let's do a quick sketch of what's going on then. So if I draw out my rod, we've got the rod AB, and we've got some wires going up. So we've got a wire going up at point D and also a wire going up at point C. I'm just going to put some lengths on here. So AC is 3 meters. This distance here is 3 meters. BD is 2 meters. And the whole rod is 10 meters long. So therefore that must be 5 meters we've got in the middle. And let's put some forces on then. So we've got 25 newtons hung from end A. So 25 newtons downwards. We've got the weight of the rod, 40 newtons. We're not quite sure exactly where that hangs because the rod is non-uniform. What we're trying to work out is the center of mass. So I'm going to say it's somewhere around here. That's my 40 newtons. And I'm going to say that this distance here is X, because I'm not sure exactly how far the 40 newtons is from C. Then we've got a tension, and we're going to have a tension up here in wire C. We haven't got to include the tension at D because the rod is on the point of rotating. So the force is pushing down at A, the rod is rotating. So at D, we can imagine that that wire is going slack. So there's no tension holding the rod up there. And we're finding the distance of the center of mass from rod A. So really I'm finding this whole distance here. I'm going to find X first and then just add 3 to it. Well, we can do the same as we did before, taking moments. And I'm going to take moments about point C because then I don't even need to include this tension in my calculations. So taking moments about point C. And again, moments going clockwise will be equal to the moments going anti-clockwise. Clockwise, I've got the 40 newtons multiplied by X. And anti-clockwise, I've got 25 newtons multiplied by the distance 3. 25 times by 3. And so I can solve that. I will get that X is equal to 1.875 meters. Now that's not my final answer, remember, that's just this distance here. The question wants the distance of the center of mass from A, so I need to add on 3. So the center of mass is, if I do 1.875 add 3, that's 4.875 meters from A. So that's my answer. 4.875 is the distance of the center of mass from end A. Okay, now that we've done those, you should be able to have a go at exercise 4E. So that's all about tilting and rotating, where the main thing to remember is if something is on the point of tilting or the point of rotating, that reaction force or the tension force in one of the supports will be going to 0.